Welcome back to the course on audio signal processing for music applications. This is the Transformations week, the week that we talk about the potential of the spectral modeling approaches we have been discussing in the past few weeks for the application of manipulating sounds, of transforming different aspects of sounds. And in these programming lectures, I want to go over some of the code of the SMS tools package that implement these transformations. So in this lecture, I want to explain the stftTransformations, so the file that implements some very basic transformations using the stft. So we'll be basically implementing this block diagram in which after the analysis of a sound in a particular frame where we have the magnitude and the phase of a sound, we can apply some transformations to this spectral data before we actually do the inverse Fourier transform and resynthesize basically a new sound. So let's go to a script that I wrote that makes a very simple operation on one single DFT of a sound on one frame. So we'll be doing some filtering to one particular frame. Okay, so we'll be using this sound, the oboe sound. And so after importing all the models and packages that we need, we read the sound file, the oboe sound file, into the array X. Then we get a window, Hanning window with a given size. Here we have the same size for the window and the one that we'll be using for the FFT, N. Okay, and then we just take one fragment of the oboe sound, 512 samples, the size that we have defined. Okay, and then we also define a filter. Okay, and the concept of defining a filter in the frequency domain is basically defining a shape in dB scale, because we're going to be applying in the dB scale that will be added to the spectrum of the original signal. So it has to be a smooth shape. We don't want to have very jagged and strong discontinuities that will create distortion. So in fact, what we are defining here is a filter that is in fact the shape of a Hamming window. So we're going to be designing a Hamming window as a filter in the frequency response. And in order to apply it in dB, we multiplied by -60 so that we have a shape. In fact, this is an invert Hamming window. So this will be used to do basically a band stop filter. So we're going to attenuate certain frequencies using this shape. We're going to see that by plotting these curves. Then we take the magnitude and phase spectrum of the signal that we chose. And in order to apply the filter, we basically decide where we're going to apply the filter. The filter is 30 samples long, so we're going to affect 30 samples of the spectrum. And we decide that it's going to be, the center is going to be the sample 40. And then now we copy the input spectrum to this MY, and we're going to manipulate, or we're going to change the 15 samples around this 40th sample. So the filter will be applied to the 30 samples that are around this 40th position. And then we do the inverse DFT. Okay, so let's run this code first. We are in this directory in the workspace, so we can just run test. Okay, so we have executed this script. Now we can keep plotting the different things. So we first can plot the waveform that we are going to be computing the DFT of. So this is the windowed fragment. Okay. We can plot the filter. So if we plot the filter, Okay, this is the shape that we're going to be applying. So in fact, it already attenuates because it's a Hamming window, so there is a step here, so it doesn't start at 0. And since we have subtracted 60 to it, it goes down to 60 and then goes up again. Okay, so this is going to be the shape, the 30 samples that are going to be applied into a magnitude spectrum. Then the magnitude spectrum that we're going to be using is this. Okay, this is the oboe spectrum of 256 samples, the magnitude spectrum, the positive values. And now the modified version, well, let's maybe we can even plot here on top of this the modified one, so we can plot the MY spectrum here. Okay, so this green spectrum is the modified version in which everything is the same except this middle part. This is the part where we applied the window, and it clearly was affected very little at the boundaries and very much at the center. So we applied a smooth shape, and therefore we did a band stop filter. We kind of attenuated the frequencies that are around this area. And of course then we obtained the output sound, which is the Y signal. Okay, this is the modified input signal. So in fact, if we plot on top of this the original signal, okay, the green one is the original signal, and of course the blue one has been attenuated, and the shape is quite different because we have attenuated certain frequencies much more than others. Okay, so this is a filtering operation that can be easily done. And then in the stftTransformations file that is within the transformations directory, we can find this code, the stft filtering, as it's implemented to be applied for a whole sound. So in fact, it's the same idea. This is the definition of the function, in which the input is the input sound, sampling rate, the window, FFT size, and hop size, and then we pass it this filter, which is an array that is going to be applied to the magnitude spectrum. And then basically the core is this while loop that does exactly what we have been showing for one particular frame. It performs the DFT, it applies the filter, and then it applies the inverse DFT. Okay, now let's talk about another operation that I believe is a little bit more interesting, which is the morphing that we talked about. So in this script, we're going to be morphing two sounds, the sound of a rain with the soprano sound, but again, one frame. Okay, in order to do this morphing, what we're going to do is apply the magnitude spectrum of one into the other, or basically interpolating the two magnitude spectra. How do we do that? Well, we do exactly the same things that we did for one single sound. We define the window, we choose these two fragments. They have to be, in this case, the same size, because we're going to be applying the same operation on both sounds. We're going to be interpolating the two magnitude spectra, so we have to start from the same window size, or at least then they have to be of the same size. Then we take the two spectra of the two sounds, of sound 1 and sound 2, and the core part of the morphing is in this next section. So what we're going to do is have one smooth version of one sound, so that we only apply the general shape of one sound into the other, and so that's going to be the second sound is going to be the one to be smooth by one given factor, 0.2. So we use the resampling, the kind of the downsampling aspect, to obtain a smoother version of the X2 spectrum. And then we upsample it again with interpolation to get the complete spectrum with a smoother representation. Of course, we can just have no smoothing by putting a value of 1. And then we're going to basically combine the two, a linear combination of the two. We are in a dB scale, so we can just add them, otherwise we would multiply them, in which there is this balance factor that defines how much of each is in the mix, basically. In this 0.7, it means this 0.7 is applied to the second sound, and the rest of 0.3 is applied to the first sound. And then, of course, we take the inverse DFT from the resulting magnitude spectrum with the phase of the first signal. Okay, so the phase will be of the first signal, and the magnitude spectrum is a combination of the two. Okay, let's run this again. Let's run test 1. Okay, and now let's keep showing the different sort of variables that we have. Let's start with the magnitude spectrum. So let's plot the magnitude spectrum of sound 1, MX1. Okay, and well, we had it open, so we have to close it here, and let's open it again. Okay, so this is the magnitude spectrum of the rain sound. So it's quite noisy. It's of course it decays in the high frequencies. So the low frequencies are stronger, but it decays as the frequencies go up. And we can plot on top of that the second spectrum, which is this soprano voice, which is clearly different. Soprano voice has these very clear shapes which relate to the formants. We are not so interested in this type of morphing to get a good resolution on the harmonics. We are interested in the general shape. Okay, and now we can plot on top of this the smooth version of the second. So we applied a smooth factor of 0.2. So MX2 smooth 2 is the interpolated version of that. So if we put MX2 smooth 2, that's going to be the smooth version of this speech, of this voice sound. Okay, so now this is the red line is the one that will be interpolated with the blue line. Okay, and now with the valence 0.7, the resulting spectrum is MY, that also can be plotted on top of this. So MY, okay, will be now is this blue line, and it's clearly an interpolation between the two. So since it's 0.7, it's closer to the red line than to the blue line. If we had, instead of 0.7, we had, let's say, 0.2 or 0.1, let's save that, and let's run the test 1 again. And now if we plot on the same plot the MY, okay, now is this purple curve, and it clearly is much closer to the rain sound because we have specified 0.1. Okay, so hopefully that gives you an idea of this idea of interpolating between two magnitude spectrum. And of course then when we plot Y, the output, this will be the resulting fragment of the sound that captures this interpolation or this morphing aspect. And if we go to the stftTransformations, and there is another function that performs that for a whole sound, the stftMorph. Okay, so stftMorph receives two sounds, x1 and x2, and here we have the possibility of controlling windowing differently. And then there is the smooth and the balance, and it does exactly what I showed in the case of two individual frames. Okay, and now we can show the file that basically is the one that is called from the interface, the transformation interface, that has one function, main, and that it receives two sounds and plots the spectrum, and it plots the resulting morphing. So it has some default parameters, and it does all the things that we have been doing. So basically for the whole sound. So it reads the sounds, it gets the windows, and then it performs the STFT analysis for the whole sound, and then it does the morphing between the two sounds. In this case, the STFT is done so that we can visualize the spectrum of the signal. Okay, and then we use the morphing, and we do again the analysis of the output sound, so we can visualize the spectrum of the input and the output sound in the plots, and then it writes the resulting sound files. Okay, so we can import this file, so the stft morph function. We can import it as a name with, for example, st, and now we can call this main, and of course we can change the parameters. So the default parameters were ocean sound with this speech mail with this particular window. So for example, let's change the valence. So now it was 0.2, so it was closer to the ocean than to the speech mail. Let's make it so that the valence of f is very much close to the speech. Let's type it right. Balance. Oh, come on. Balance. Okay, f. And let's put, for example, 0.9. Okay, and let's run this. Okay, so now we have the input sound, the spectrogram of the input sound, and this is the spectrogram of the output sound. Okay, and then the actual output sound. So clearly here the output sound has captured quite a bit of the shape of the speech. So if we can play it, it has saved a file into this directory, so we can just type play and ocean stft morph.
Do you hear me? They don't lie at all.
Okay, so clearly it has taken the duration of the ocean sound, because that's the basic sound from which we are taking the analysis from, and then the magnitude spectra has been modified by this smooth spectra of the speech mail sound. Okay, and that's all I wanted to say. So we have seen how within the SMS tools there is all this code for being able to do morphing between two sounds using the short time Fourier transform, and the code is quite simple. In fact, is maybe the simplest type of transformation that we can do with these spectral tools, and it can be quite useful and interesting for quite a few types of applications. So that was all. This is the first programming lecture. So in the next one, we will talk about the sinusoidal model, how to implement transformations in the sinusoidal model using these same SMS tools and the particular code that implements them. So I see you next class. Bye-bye.